we met in the previous lesson. It's a formula for raising a power of a complex number, provided the complex number is in the form r brackets cos theta plus I sine theta, r being the modulus, theta being the argument. R cos theta plus I sine theta to the n is r to the n brackets cos n theta plus I sine n theta. So that's De Moivre's theorem. Last lesson, we saw how to use that to do powers of complex numbers. Today, what I'm going to do is to show you how to use De Moivre's theorem to prove a very specific type of trigonometric identities. And what we're interested today is identities for, identities where on the left-hand side, you've got cos n theta, sine n theta or tan n theta, where n is an integer. So for example, a formula for cos 4 theta, or a formula for sine 5 theta, or a formula for tan 6 theta. There is a specific method for doing this, and generally these questions have two parts. In the first part, you will prove an identity of this type using De Moivre's theorem. I'm going to do that today. And then in the next lesson, we will do applications of this process. We will see alternative questions we can do with these. Now, the method is going to combine De Moivre's theorem with a bit of classic A-level mathematics, which is the binomial theorem. So that's also on the formula booklet, the rule for expanding a plus b to the power of m. Now, what I'm going to do is go through example 1 with you, but can I strongly encourage you to change, to add something to the question. The point of example 1 is to prove the following identities. I am going to prove that cos 4 theta is given by this expression, 1 minus 8 cos squared theta plus 8 cos to the 4 theta. Please write that down. I'm going to prove that sine 4 theta is given by 4 cos theta sine theta brackets 2 cos squared minus 1. And I'm also going to prove an identity for tan 4 theta. I'm going to prove that tan 4 theta is given by 4 tan theta minus 4 tan cubed over 1 minus 6 tan squared plus tan to the 4 theta. In an exam question, it is highly likely that you would only be proving one of these identities. And how I'm going to do this is the following. So I'm going to copy what it says in the first bit, expand and simplify cos theta plus I sine theta to the power of 4. Well, why am I going to do that? Well, by De Moivre's theorems, if you go back to De Moivre's theorem here, let me just make my head a bit thicker. If you first of all get rid of r, so replace r with 1, De Moivre's theorem says that cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. That's taking De Moivre's theorem and getting rid of r, replacing r with 1. So what I'm going to do is the following. If I write that down in the case where n is equal to 4, I know that cos of 4 theta plus I sine of 4 theta is equal to cos theta plus I sine theta in brackets to the power of 4. So that's De Moivre's theorem in the case where n is equal to 4 and getting rid of r, making r equal to 1. Okay, so that's what you do. Replace r with 1, write down De Moivre's theorem using the value of n, which occurs in front of the thetas. And what I'm going to do in a second is I'm going to do a binomial expansion on the right-hand side. Now, before I do this, there is a sensible abbreviation to use, because expanding this, it's going to get very, very big, because it's got cos thetas and sine thetas in it. So I'm going to rewrite this as c plus is to the power of 4, where c is an abbreviation for cos theta and s is an abbreviation for sine theta. You don't have to do this, but it will cut down on the writing. So I'm going to expand the right-hand side, c plus is to the power 4. So by the binomial expansion formula, if we expand a plus b to the m, the first term is a to the n, then n choose 1, a to the n minus 1b, etc., etc. So this is what it's going to give me. So the first term is c to the 4. The second term is 4 choose 1. Can I remind you where to do that on your calculator, ladies and gentlemen, boys and girls? So if you press math, no, you don't. If you press option and then you press F6 and it's under probabilistic, you get NCR. 4C1 is just 4. So N4C1 is 4. A to the n minus 1 is c cubed and b is is. The next term is 4 choose 2. If you go back and change 4 choose 1 to 4 choose 2, you'll get 6 c squared times is in bracket squared. The power of c goes down, the power of is goes up. The next term, 4 choose 3 to 4 choose 3. Change that into a 3. You get 4 c times is cubed. And then the final term is is to the power of 4. So that's doing a binomial expansion of cos plus I sine to the 4. I'm now going to simplify this by considering powers of I. So the first term is just c to the power of 4. The next term is 4 times c cubed times is in a bracket. That bracket doesn't really do anything. I can move the I to the front. That is 4i c cubed s. Now the next term is as follows. I have got is in brackets squared. When you expand that bracket, you'll get I squared x squared, and I squared is minus 1. So this next term is 6 times c squared times minus s squared, which gives you minus 6c squared s squared. In my next term, when I expand the bracket, I'm going to get is cubed, which is I cubed s cubed. Now, I cubed is I times I squared, which is therefore minus I, because I squared is minus 1. So this term becomes minus 4ics cubed. And then the last term is I to the 4 times s to the 4. I to the 4 is I squared squared, which is minus 1 squared, which is 1. So that just gives me s to the power 4. So that's really what I've done in part A. I've expanded and simplified this. What I'm now going to do in part B is to use this to prove these three identities that we do. Now, this is how I can do this. If I compare, I've got that equals all of that. I can write down an equation for cos theta and an equation for sine theta by comparing the real and imaginary parts. Maybe I'll choose a different color for this. Maybe I'll go in blue. So if I look at the real parts of both sides, I will get cos 4 theta is the real part of this. The real terms on the right-hand side are c to the 4 minus 6c squared s squared plus s to the 4. The other two terms have a coefficient of I. This gives me cos 4 theta equals c to the 4 minus 6c squared s squared plus s to the 4. And if I was just looking to prove the identity for cos 4 theta, I would now do some algebra with this to turn it into that. To get the formula for sine 4 theta, you compare the imaginary parts. Maybe I'll do these in green. So if you look at the imaginary parts on both sides, the imaginary term on the left-hand side is sine 4 theta, I times sine 4 theta. The imaginary terms on the right are that and that. So comparing the multiples of I, comparing coefficients, we get that sine 4 theta is equal to 4c cubed s minus 4c s cubed. Let me now get these two identities. So the first one I want to prove is the identity for cos 4 theta, which is given here. So I already have this formula for cos 4 theta that I have deduced here. The answer which I'm trying to turn it into only involves cos, c. Whereas this current expression has got c and s, it's got cos and sine. But that's okay because we connect c squared and s squared, cos squared and sine squared, because sine squared is 1 minus cos squared. So I can write down that, maybe I'll go back to blue, that cos 4 theta is equal to cos to the 4 theta is c to the 4 minus 4 6 c squared times sine squared, which is 1 minus cos squared. So that's 1 minus c squared. And then plus sine to the 4. Well, sine to the 4 is sine squared squared, which is 1 minus cos squared squared. If we now do some algebra, we should be able to derive this identity here. So this is going to give me c to the 4 minus 6c squared plus 6c to the 4. And then if you expand 1 minus c squared all squared, you will get 1 minus 2c squared plus c to the 4. And if you collect together the like terms in the order that was given above, the constant term first. The constant term is 1. I've got minus 6c squared minus 2c squared, which is minus 8c squared. And then I've got c to the 4 plus 6c to the 4 plus c to the 4, again, is 8c to the 4. So therefore, I have proved the first identity. Cos 4 theta is 1 minus 8 cos squared theta plus, 8 cos to the 4 theta. That's the first identity proved. That's because C stands for cos 4 theta. If I then want to do the second one, get the identity for sine 4 theta. So I've already got an identity for sine 4 theta, but I want to rewrite it as 4 cos theta sine times 2 cos squared minus 1. That's what I'm looking for. Well, I can write down the formula I've got for sine 4 theta already. That's what we've got. So we already know that's true. I want to turn it into that expression. I'm going to factorize it and then see what we get. So I know that, this is for my second one, sine 4 theta is equal to, here's my previous formula, 4c cubed s minus 4, it should be, something's gone wrong there slightly. Yeah, 4c cubed s minus 4cs cubed. So that can be factorized as 4cs into s squared minus c squared. 4cs in front. So that's 4 times cos times sine squared minus cos squared. The expression which I'm looking for has 2 cos squared minus 1 in it. So I'm going to get rid of the sine squared in front. So that's the same as 4cs into sine squared is 1 minus cos squared, take away cos squared, which gives me 4cs into 1 minus 2c squared. So that proves the formula for sine 4 theta. Sine 4 theta is 4 cos theta sine theta brackets 1 minus 2 cos squared theta. That's the formula I was looking for. Okay. And then finally, I want to prove the identity for tan 4 theta. Now, I'm just going to clear off what I've done so far to give myself a bit of space. And then I'll do the third one to get the identity for tan 4 theta. So if I can remove what I've done here. So the identity which I'm looking to prove for tan 4 theta is given here. Earlier, I wrote down formulas for cos 4 theta and sine 4 theta. To get the expression for tan 4 theta, you want to divide those two formulas, and you need to do that before you start simplifying them using sine squared plus cos squared is 1. So this is how I can get my formula for tan 4 theta. So by standard trig identity results, we know that tan 4 theta is sine 4 theta divided by cos 4 theta. And I've already got my expressions for sine 4 theta and cos 4 theta. It's the unsimplified forms you want to use. So that is 4c cubed s minus 4cs cubed, all divided by c to the 4 minus 6c squared s squared plus s to the 4. So this is an identity for tan 4 theta, but the identity which I'm trying to prove is this one that only has tans. Oh, sorry, there's an S. Sorry, I've done that like twice there. 4cs cubed, that's what that should be there. Sorry. So in order to do this, this is what I'm going to use. I know that sine over cos equals tan. So maybe I'm just going to write this out in terms of sines and coses to make it clearer what I'm going to do. So my current expression is 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta, all divided by cos to the 4 theta minus 6 cos squared theta sine squared theta plus sine to the power of 4 theta. Now what I'm going to do is the following. Nice things happen. We know that sine over cos equals tan. There are 5 terms in this equation, 2 on the top and 3 on the bottom. Each of them is effectively the product of 4 trig functions, some combination of sines and coses. If you divide the top, I'd like a plus. Why would I do that? If you divide the top by cos to the 4 theta and divide the bottom by cos to the 4 theta, the value of the fraction stays the same because we are dividing top and bottom by the same thing. Now, if you look at each term on the top, 4 cos cubed sine divided by cos to the 4, the cos cubes cancel out. You get 4 sine over cos, which is 4 tan theta, minus 4 cos sine cubed divided by cos to the 4. Cos cancels out on the top and the bottom. Sine cubed over cos cubed gives me tan cubed. So that is 4 tan cubed theta. And we do the same on the bottom. Cos to the 4 divided by cos to the 4 is just 1. 6 cos squared sine squared over cos to the 4. Well, cos squared over cos squared cancels out. 6 sine squared over cos squared gives me 6 tan squared theta. And the last term is sine to the 4 divided by cos to the 4, which is tan 4 theta, and we are done. Now, just to remind you, folks, in an exam, it is highly likely that A, you would only be required to prove one of the 3 identities that we've done. And it's also likely that there would be a part B, which requires you to do something else with the identity. We'll worry about that more in the next lesson. So for now, folks, here's a summary of what we've done here, ladies and gentlemen, boys and girls. This is the method to prove a trig identity for cos n theta or sine n theta or tan n theta in terms of powers of sine, cos and tan using de Moivre's theorem. And in a further maths exam paper, if they want you to use this method, they are going to tell you you have to do it via de Moivre's theorem. There are ways to generate these identities without doing that, but that's what they're going to want you to do. So here's what you do. Step 1 is you write down cos n theta plus I sine n theta is cos theta plus I sine theta to the power of n, where n is the number in front of the theta in either cos, sine or tan. Step 2, hopefully using the abbreviation C is cos, S is sine, you expand the right-hand side using the binomial expansion formula. Step 3 is you simplify using I squared is minus 1, I cubed is minus I to the 4 is 1, etc. And then step 4, you can split it into 2 separate identities. Cos n theta is the real part on the right, sine n theta is the imaginary part on the right. All of those steps 1, 2, 3 and 4 you will always do. Then you either do 5 or 6 depending upon what you are looking for. If you want an identity for cos n theta or sine n theta in terms of cos or sine, you will already written down an identity. You are probably going to have to simplify it by using sine squared plus cos squared is 1. Conversely, if you want an identity for tan n theta, use tan n theta is sine n theta over cos n theta to get an identity for tan n theta in terms of sines and coses. It will always be the case that if you divide the top and bottom by cos to the n theta, all of the sine and cos terms will turn into tan terms. So students, here's what I like to do is pause the video. There's a question on the next page for you to have a go at. Pause the video, have a go at this, and then check your answers. Okay, folks, so here's my solution. So to get an expression for cos 5 theta, and by an exam, it's highly likely to be a show that question, by the way. For cos 5 theta in terms of cos theta, start off with cos 5 theta plus I sine 5 theta is c plus I s to the 5, where c is cos theta and s is sine theta. If you're going to use this abbreviation, which you don't have to do, please explain that c is cos theta and s is sine theta. Then expand the right-hand side by the binomial expansion formula. You'll get this. And then that's using the fact that 5c1 is 5, 5c2 is 10, etc., etc. Then simplify the powers of I. You get this expression, c to the 5 plus 5ic to the 4s minus 10c cubed s squared minus 10ic squared s plus 5c s to the 4 plus I s to the 5. That's because I to the 5 is just I. If you compare the real parts, which is all we need to do in this case, we just want a formula for cos 5 theta, you will get cos 5 theta is c to the 5 minus 10c cubed s squared plus 5c s to the 4. Now, because this wants to be written only in terms of cos theta, I need to get rid of the s's, which stands for sine theta, but sine squared is 1 minus cos squared, so s squared can be written as 1 minus c squared. So this is c to the 5 minus 10c cubed bracket 1 minus c squared plus 5c times 1 minus c squared, whoops, in brackets squared. By some straightforward algebra, if you expand all of that, you should get c to the 5 minus 10c cubed plus 10c to the 5. If you expand the final term by squaring out the bracket and then multiplying it through by 5c, you should get 5c minus 10c cubed plus 5c to the 5. If you collect like terms, you'll get that, 16c to the 5 minus 20c cubed plus 5c. So consequently, my answer is 5 cos 5 theta is 16 cos to the 5 theta minus 20 cos cube theta plus 5 cos theta, and we are done. You are now in a position where you can do the next the exercise on this. In the next lesson, we'll do some harder questions where in the first part you prove an identity of this type, and then in the second part you use that to solve a subsequent problem.